we we have analyzed quantitative data. That was way back at the beginning of the year by finding mean, standard deviation, median, IQR, etc. And then we did inference involving quantitative data, specifically means. Okay. We also looked at categorical data at the beginning of the year when we did two-way tables, things like that. And then we also did inference for categorical data, and the main measuring stick we used for inference was proportions. Okay. Way back in chapter 3, we talked about the relationship, analyzing the relationship between two quantitative variables. And we did something called linear regression. Now we're going to take that and do inference for it. Because remember what we did scatter plots that showed the relationship. We were able to describe the relationship using 4 components. Then we put in a least squares regression line. And then we were able to further analyze it from that. So basically what we're going to talk about today is when we have a situation like that, okay, how well does, like, we're going to do inference to see, is there actually a relationship between two quantitative variables, or is there not a relationship? So the example we're going to look at today are gun ownership versus gun homicides in different countries. So here you see a bar graph with several countries where the x-axis represents the country and the y-axis represents the number of homicides per 1 million people. And you can see for several countries, it's below 5 gun homicides per 1 million people, and yet there's one that's way up here at 45. Can you guess what country this is? It would be America. It would be the USA. Okay. So, and as you're probably familiar, because of a certain amendment in the US, that people are allowed to own guns. Okay, and quite a few people in the States own guns. And as a result of what was happening, what the gun ownership, the high gun ownership in the States, the gun homicide rate is quite high. Okay? Whereas for other countries who may also have higher gun ownership rates, is not high. So something's going on in the States. So the debate is gun control versus gun rights. Okay? I mean, several people are like, okay, the more people that own guns, the more the risk that people are going to die from guns. And you can point to the US as an example. However, many people in the US argue that, well, if more people own guns, then more people will be protected or will be able to protect themselves, and they'll be, so they'll be able to protect themselves from gun homicide. That argument doesn't seem to be working too well, but it is two arguments that are presented in the States. Okay? So, make sure. Stronger gun laws. Prevent guns getting into the wrong hands. Therefore, preventing gun violence. And that seems to work in a lot of countries. The other argument is if more people own guns, it would deter criminals from committing gun crimes. And if it's hard to tell from the bar graph at the top, but on the second page, all the numbers are listed for those countries. And you can see that I'm just going to use two countries as examples where stronger gun laws prevent guns getting into the wrong hands. Japan seems to be a very good example. And if more people own guns, it would deter criminals. Germany actually seems to be a good example of that. The US does not. So you can see here, we've sampled 19 countries, okay? And if you look at Germany, you can see the civilian firearms is quite high, the highest of all these ones that were selected. And yet the gun homicides are below 1 per 1 million. If we look at Japan, we see that it's quite low, the lowest of all the sampled countries. And its gun homicides is even lower. So what's the best way to visualize all this data? Put it on a scatter plot. We use scatter plots to analyze the relationship between two quantitative variables. And from that, we can put in a least squares regression line. And instead of us worrying about calculating a whole bunch of measures that we're going to need, if you recall, we had a computer output do it for us. And when we did the computer output in Unit 3, we really focused on this to create the equation and these two to talk about the variation. That was Unit 3. In this lesson, we're going to talk more about using these, because these are the values we need to do inference, either do a confidence interval or a hypothesis test. Okay, so again, random sample, 19 developed nations, each nation's firearm ownership rate, and then their gun homicide rate. Remember, one thing that you were asked to do when we talked about the relationship between two quantitative variables is one's explanatory and one's response. How can you tell which is which? Well, you can always tell by, like, you'll be given a scatter plot, okay? You'll be given a scatter plot in situations like this. So, sorry, scatter plots here. The x-axis, that will be the explanatory. Okay. Explanatory x. So it would be civilian firearm ownership rates. And therefore, the response would be the variable on the y-axis, be the gun homicide. And another way to talk about this is that the explanatory predicts. Okay. So we are trying to see, we are looking at how well civilian firearm ownership rate predicts gun homicide. That's another way you can tell between the explanatory and response. Okay, so here we have Japan is very low. So Japan is here. And Germany is still low, but it has a high X value. What was it? I think it's, was there one? Oh yeah, Switzerland was higher. So Germany's here. Okay. So other locations in these graphs relate to gun control versus gun rights arguments. Well, Japan would be pro ownership. It's the low homicides. No guns to commit crimes. Germany argues high ownership leads to low homicides because it acts as deterrence to criminals. If you recall, when we talked about looking at the relationship between two quantitative variables using a scatter plot, we use the acronym DOS, where this was direction, as in positive or negative. This was the existence of any outliers. This was form, linear or nonlinear, or curve. And this was strength. How well, or how much of a line do the dots in the scatter plot form? Okay. We are only asked the direction and strength. What's the direction, positive or negative? Look at the scatter plot. Positive. what's the strength? And remember we said like strong, moderate, weak. Moderate? What do you think? I mean, this would give us more information, but assume we don't have this. Assume we're just looking at this. There seems to be a fair amount of spread, doesn't there, around that regression line? Like there's a few that are quite higher. There's some that are quite lower. So definitely no more than moderate. I would even go as far as saying weak. Slightly moderate. Which tells us something right there that, you know, perhaps there isn't much of a relationship between the two. But that's not proper inference. We have to go further. Okay. Now, another thing we did is we came up with an equation for the line that we're using to fit the data called the least squares regression line. And this was the general formula, y equals a plus bx, where this was the predicted y, not the actual y, but predicted. This was the y-intercept. This is the slope. This is the explanatory. And this is the predicted response. And we can actually get this equation from the computer output. Okay. So let me just erase this stuff here so clear things up. So to get the equation, we use these two numbers. Okay. We use these two numbers. But constant, that means the y-intercept. The x, that means the slope, the number that goes in front of x. So our equation would be y hat equals 0.91618 plus 0.04675x. So that would be our equation, is y hat equals the y-intercept of 0.91618 plus the slope 0.04675 times x, the value of the explanatory variable. And remember, when we had least squares regression equations, you were asked to interpret the values. So what does the slope mean again in the context of the question? It tells you the amount increase or decrease of the y, predicted y, for every 1 unit of the x. So we would say the model predicts the increase of, and then the slope 0.04675 gun homicides. Gun. for every 1 unit increase in gun ownership rates or in, let's say, civilian firearms. This is just kind of reviewing what we did in Unit 3. Because now we're actually going to say, okay, how good is this line? Does this line actually show a relationship? Can we make a conclusion? And remember, there's two ways that we can determine, and that's either using a confidence interval or a hypothesis test. So we're going to do both. And what we use to help us, which you'll always get in the question, you'll see momentarily. Okay? And because we're dealing with quantitative values, okay, remember we use t-intervals and t-tests. We only use Z if we are dealing with categorical, like something that involves a proportion of something. Okay? And the nice thing is that the computer output, which you'll be given, calculates everything for you, which we'll see. So let's look at constructing and interpreting a 95% confidence interval for this regression line. We want to see if we can apply this sample that we took to the population, as in all countries. So that's our population, is all developed nations. And the sample that we took were 19 of them, random. Now, what we are measuring, what we're actually going to focus on to make our inference is the slope. Okay? So the parameter is going to be, and you've seen this Greek letter before, beta. That represents the population. So that's the true slope for regression. For all nations. And what we're going to use as our sample slope, well, we use it in the equation, little b. It's the sample regression slope. Remember, that was 0.04675. Okay. So we're calling what a confidence interval is. Remember, we take our sample, okay, our sample statistic. We have a margin of error that, depending on the confidence level, the population parameter will fit into. So here we have our sample slope that we took from the 19 nations. We're going to have a margin of error, a certain amount above, a certain amount below. And we want to be 95% confident that this interval here is going to capture the true one. So maybe it's here, maybe it's here, maybe it's here. And how did we do that? Well, this is, and you're given this on your formula sheet. To calculate a confidence interval, we use the test statistic, okay, or the sample statistic, plus or minus the margin of error. How do we calculate the margin of error? Well, we calculate it by calculating the standard error, but it's going to be given to us in that computer output. And the critical value, how many standard errors away, right? That we're going to have to use our graphing calculator. So if this is the general formula for a confidence interval, for a regression slope, it's going to be this. So this is going to be the sample slope that we have from our computer output. This we're going to have to calculate, okay? So, and I've said here we have to calculate it. This is the standard error of the sample slope. Okay, so you can just add this. You'll see this on the computer output, and you will see this on the computer output. So from that computer output on the previous page, remember the slope was 0.04675. To find the standard error, it's the one in blue here. And look at the column title. It says standard error, and then you go to the slope row, and that's the number. So it's 0.02625. So we've got b, little b, we've got the standard error of little b, we just have to calculate t. And remember, to find the number of standard errors away in a 95% confidence interval, which means 95% of the distribution is covered, we have to use inverse t on our graphing calculator. So if you think about it like this, okay? This is 0. This is 1 standard error, 2 standard errors, whatever. We have to find, so this is 95% here. We have to find this value. It's going to be negative, so we change it to positive. Had to get 2.5. The area is 2.5. Yes. Yes. So remember, so if this is 95%, these two are 5%, which means this one, yes, is 2.5%. So we want area below confidence interval of 95%, which is 2.5%, or 0.025. When you do inverse t, you're going to be asked degrees of freedom. Now remember, we said degrees of freedom was normally the sample size minus 1. Here it's going to be the sample size minus 2. So it's going to be n minus 2. The sample size is 19. So 19 minus 2, the degrees of freedom will be 17. So on your graphing calculator, second bars, because we're doing an inverse t. Inverse t, the area is 0.025. The degrees of freedom is 17. Hit enter a couple of times, wait for it to calculate, and you get approximately negative 2.11. So that's about negative 2.1, but we just want to find the number of standard. Yes, this is negative 2.11, but it's 2.11 standard errors away from here. So we just changed it to positive. So T star is just going to be positive 2.11. And now we're ready to do our confidence interval. So it's going to be 0.04675 plus or minus T star, which we've calculated to be 2.11, times the standard error of little b, which is 0.022625. So if we do 0.04675 minus 2.11 times 0.2625, we get negative, and I'm just going to round this one, so negative 0.009 you should get. Okay. And then we would do 0.04675 plus 2.11 times 0.02625, and that will give us, if we go to 3 decimal places again, positive 0.102. So that means we can say we are 95% confidence. Confidence. The interval 0.009 to 0.102 captures the true regression slope. Stacking this one. Or the millennium one. Looking at the confidence interval, would you say if there's a relationship or no? If there's no relationship, what would the slope be? 0, right? Because if you think about when we talked about R, the correlation, nothing means there's no relationship. So 0's in our interval. So we can't say that there is a relationship between gun ownership and gun homicide rates, according to the sample we have. Okay. What about a t-test for the same thing? Again, you're going to get the value. You actually don't have to do any graphing calculator stuff here. Okay. It's going to be all on the computer output for you. And it's going to be under these 2 columns. Your t statistic, which you don't really need. Okay. This is the one, the p-value. Okay. That's the one we want to look at. So remember, we state our hypotheses, HO and HA. And remember, we're talking about the populations here. So the slope, the default means no relationship. Slope, the true regression slope is 0. If there is a relationship, whether positive or negative, we don't know. That's why we put not equals to. We're not saying it's greater. We're not saying it's less. We're saying it's different than 0. And then, of course, you have to define this true slope of population regression line.
Is that in the context?
Pardon me?
Is that in the context when you're showing that failure? Or do you have to say it?
Hang on, I'm not done.
I'm
True slope of population regression. No, you're right. Relating gun ownership rates to gun policies. What's the interpretation? Well, HO or the null? No relationship. In gun ownership. And homicide rates, or gun homicide rates. Gun homicide. And HA for the alternative research. Is a relationship between gun ownership and gun homicides. Yeah.
What could be two questions? Is there a reason you didn't want to say it's or you just
It's not a big deal. I've seen both actually. So why do we use the population parameter instead of the sample? Because we are hypothesizing about the population. About the population. We don't know about the population. We don't have to hypothesize about the sample because we know everything about the sample. And I briefly mentioned this last one. Why do you think the above test is the same thing as testing if there's no correlation? Well, if there is no correlation, there is no relationship, or there is a completely scattered plot. Doesn't form any. The dots just sort of look randomly plotted. So like I said, we can use the interval to actually make a conclusion on this test. Because there is a relationship between confidence intervals and hypothesis tests. Okay? And remember what I said, what did I say? Negative 0.009 to positive 0.102, was it? 102? Did I have? Thank you. Zero in interval means no relationship. It's plausible. Plausible outcome. But like I said, because we're doing a hypothesis test, we want to focus on the p-value. Like, don't worry too much about the test statistics. Focus on the p-value. So if you remember the p-value from the computer table, a computer output table you were given, we would say because our p-value and from the computer output it was 0.0928 is greater than alpha, or our alpha value, we fail to reject HO. We don't have convincing evidence. Of a linear relationship. Gun ownership and gun homicides. So notice it's very to what we have been doing with proportions and means. Just to see what would happen if the US happened to be included in that random sample. How much of an impact that would. Okay, so sort of gone through everything here in detail for a confidence interval for slope and a hypothesis test for slope. But once again, you can use the four-step process. So we've pretty much gone over everything that we're going to do here, except for the conditions. That's one thing we didn't talk about yet. Okay, so if you see a question like this, it is highly likely you're going to be presented with all of this. Obviously, a scatter plot. Okay. Obviously, a computer output. We need those, okay, for the, not only for the actual context, but also for the measures we're going to use for a confidence interval or hypothesis test. We're going to need these things for our conditions. If you remember a residual, what is a residual? A residual is the difference. This is a residual. And a residual can be positive or negative. It's the difference between an actual value and its predicted value. So here's the actual value for this country, okay, the actual gun homicides. But here's what is predicted. The difference between those two is the residual. And therefore, we can graph all the residuals. We can also show a histogram, which is a range of civilian firearm ownership, rather than just putting each individual one in. A histogram saves us a little bit of time. We're going to need this for conditions as well. So we'll talk about these when we get to the next page when we talk about conditions. So we're going to do both at the same time. So here, the state for each. Well, we've already done this. We've already done this when we did it, when I showed you the detailed way. Estimating beta with 95% confidence. Where beta is true slope of regression line relating gun ownership and gun homicides. So that was the state confidence interval. Our state hypothesis test. No relationship is the null. There is some relationship is the alternative. And beta equals, I'm not going to spend a bunch of time writing this again. It's the same thing. The true slope of a regression line relating. Okay, conditions, you are used to 3. This one has 5. Think of the word linear, almost linear. Now, 3 of them are the same 3 as what we've done before. We've just added 2. Okay. So the first one, which is new, is linear. We have to establish that there is a linear relationship between the two. And to do that, we look at the residuals. And we've done this before. If there is a leftover curve pattern in the residuals, that means linear is not a good fit. We stop. If it's randomly scattered about, same amount above, same amount below, linear is a good fit. So if we look at ours, we're pretty scattered about. Same amount above, same amount below. This tells me the linear condition is met. Independent, that's when we do, is our sample size less than 10% of the population? Well, is 19 nations less than 10% of all nations in the world? Yes. Normal, it's either, remember, we're dealing with means, so it's large sample, not large counts. Your sample size has to be greater than or equal to 30, which this one is not. Or your sampling distribution has to be approximately normal with no outliers. Well, this has got a bit of a skew, but we can get away with saying it's approximately normal. So even though n is less than 30, the sample size, our sampling distribution is normal, so we can say, because remember, it's not just large sample, it's normal / large.
Does that mean one or the other?
What's that?
Does that mean one or the other? Like, it cannot.
As long as it means one. Yeah. Okay, this one's new. And this involves the funkiest word in statistics, if you can pronounce it. Equal standard deviation. That's what obviously, or hopefully you know that means standard deviation. We have to check the residual plot again to see if it shows little heteroscedasticity. And what is heteroscedasticity? Well, it means that, and you can see it down here, okay? If the variation increases for a certain value at certain values of x. So notice what happens here. The variation is pretty low, right? But as x gets higher and higher, the variation starts to increase. This violates this. It has to be pretty uniform in order to meet that condition. So if we go back to the scatter plot, sorry, the residual plot, yeah, it starts to widen a little bit, but not very much. It's fairly uniform. So we can say that condition is met. And the final condition, we've seen before, random. Was the sample randomly selected? Okay, so going back to our two. For the plan, we're going to do a t interval for slope, or a t interval for beta. And for the other one, we're going to do a t-test for slope. Conditions I'll put for both. So linear, no leftover curve pattern. In residual plot. So that means linear is met. Independent, or 10%, I won't call it independent. Well, they call it independence at the line of fits. So 10%. 19 is less than or equal to 0.10 of all nations. Met. Normal. Even though $19 is less than 30, histogram is approximately normal with no strong skewness or outliers. Matt. Equal standard deviation. Residual plot shows similar scatter as x increases. not widening or narrowing. Next. Random. The nations were randomly selected. What's that? Two, well, we've already done this. Okay. We established that T star was 2.11 by using inverse T. And then to find the confidence interval, it was what we did before. So it was 0.0, forget those exact numbers. 4675 plus or minus 2.11 times 0.02625, which gave us, and we said it was approximately negative 0.009 to 0.102. That was the confidence interval. The do phase, this is even easier. The p-value from the computer output was 0.0928. So therefore, conclude for both, which we've already done. We are 95% confident. The interval negative 0.009, 0.102, captures the true regression slope relating gun ownership gun homicides and finally conclude as our p-value is less than alpha, fail to reject HO. Don't have convincing evidence. On a relationship. in gun ownership. And gun homicides.